Fundamental theorem of algebra basically says a polynomial f of x of degree n greater than 1 has at least one complex zero. Remember, complex numbers are written in the form a plus bi. Remember also that complex numbers include both real numbers and imaginary numbers. So, the polynomial function of degree n has at most n distinct zeros. We say at most n distinct zeros because there could be some multiplicity to them. Let's look at an example. Write a polynomial of degree 4 with leading coefficient of 6 and zeros of 2, 5, 3i, and negative 3i in completely factored form. We know completely factored form is a times, in this case, x minus c1, x minus c2, x minus c3, x minus c4. We know there's only 4 because it gives us the 4 zeros. So this is 4 times x plus 2 times x minus 5, x minus 3i, x plus 3i. When we FOIL the x plus 3i and x minus 3i, we get x squared plus 9. When we FOIL the x plus 2 times x minus 5, we get x squared minus 3x minus 10. Now we need to multiply this trinomial times this binomial. X squared times x squared is x to the 4th. We're going to then do negative 3x times x squared is negative 3x cubed. X squared times 9 is 9x squared. Minus 10x squared is negative x squared. We then get negative 3x times 9 is negative 27x, and finally negative 10 times 9 is negative 90. And the last thing we have to do is distribute the 4. This becomes 4x to the 4th minus 12x cubed minus 4x squared minus 108x minus 360. Now, notice that we have the 3i and the negative 3i are conjugates. And when we have both of them, when they multiply out, we wind up with still having real coefficients. And this leads to our conjugate zero theorem. If a polynomial has real coefficients, and if a plus bi is the zero of f of x, then the conjugate a minus bi is also a zero of f of x. In other words, if you have one, you have to have the other as long as all the coefficients are real numbers. In other words, there's no i's included in the coefficients. Let's look at an example. Find the zeros of f of x equals x to the 4th plus 10x squared plus 9 if one zero is negative I. Notice I have 1, 10, and 9 as coefficients, so they're all real. So if negative I is a 0, that means I is also a 0. And if negative I is a 0, that means x plus I is a factor. And if I is a 0, that means x minus I is a factor. And when I multiply the two, x plus I times x minus I, that means you get x squared plus 1 is also a factor of the polynomial. So I can take this original polynomial and divide it by x squared plus 1, which is what we're going to do here. We're going to do x squared plus 1. We will put in 0x as placeholders. This becomes x to the 4th plus 0x cubed plus 10x squared plus 0x plus 9. Again, the 0x cubed and the 0x are placeholders. We do the same thing we did before. We concentrate this x squared out front. How many times is x squared? Going to x to the 4th, it goes in x squared times. I line these up so that these columns all have the same amount. So x squared times x squared is x to the 4th plus 0x plus x squared. Again, I subtract. 10x squared minus x squared is 9x squared. Bring down 2 of these because I have 3 terms out here. So 9x squared plus 0x plus 9. How many times does x squared go into 9x squared? 9 times. Again, we multiply. 9x squared, 9 times x squared is 9x squared plus 0x plus 9. We subtract these. We wind up with 0. So that means this entire polynomial I started with factors to x squared plus 1 times x squared plus 9. We know the x squared plus 1 factors to x minus 1, x minus I, x plus I. The x squared plus 9 factors to x minus 3i, x plus 3i. So the zeros are I, negative I, 3i, and negative 3i.